This is part 4 of the lecture on statistical inference. In the last few sections, we studied p-values and confidence intervals for coefficients of linear regression models. But, there are a few other types of statistical testing for linear regression. So far, we have been studying statistical test for each of regression coefficients. But there is a statistical test for 2 or more regression coefficients together. Let's look at Model 2. This regression model has 3 independent variables x1, x2, and x3, so there are 3 regression coefficients, beta 1, beta 2, and beta 3. As we have learned, we can set up a null hypothesis for each of these 3 betas, beta 1 equals 0, beta 2 equals 0, and beta 3 equals 0, which will lead to 3 different p-values. But, we can set up a null hypothesis about 2 or more betas together, for example, both beta 2 and beta 3 are 0. Why do we want to set up this kind of null hypothesis? Actually, this approach is quite useful, particularly when a polytomous categorical variable is included in the regression model as a set of binary variables. Suppose y is some dependent variable, x1 is age, and x2 and x3 are binary variables for education categories. For example, x2 may be for those who have not graduated from high school, and x3 may be for those who have graduated from high school, but not college. We can start with a simple linear regression analysis of y on age, like Model 1 in this slide. Then, we may want to add education to this analysis, like Model 2. In such a case, we may want to make sure that it is worth including education to this model. So we may want to test a null hypothesis that implies education makes no difference to the dependent variable, controlling for age. Let's look at this example of multiple linear regression of fasting blood glucose level on some demographic variables including race ethnicity. 2 slightly different regression models were set up. Let's call them Model 1 and Model 2. The difference is, in Model 1, non-Hispanic Black was chosen as the reference category of race ethnicity, but in Model 2, non-Hispanic White was chosen. This table shows regression coefficients and p-values for race ethnicity categories from the 2 analyses. In the results of Model 1 analysis, race ethnicity may not appear to be a very important independent variable, because the p-values are 0.170, 0.183, and 0.639, so none of the p-values is very small. But, in the results of Model 2 analysis, race ethnicity looks more important than in the results of Model 1 analysis, because, now the p-value for Hispanic is 0.006, which is very low. Why is there such a difference between the 2 sets of results? It is because the largest racial ethnic difference in fasting blood glucose level exists between Hispanic and non-Hispanic White. But, in the Model 1 results, there is no p-value for the difference between Hispanic and non-Hispanic White, because neither of them was the reference category. So results of the regular statistical test for polytomous categorical variable could look different, depending on the choice of the reference category. This problem can be solved by setting up a null hypothesis involving all of the binary variables for race ethnicity categories together. The joint statistical test for multiple variables is useful for assessing the overall importance of a polytomous variable in regression analysis. In this case, the null hypothesis is betas for all of the categories of the polytomous variable, except the reference category, are 0, which implies that the polytomous variable makes no difference in the dependent variable. So the rejection of the null hypothesis means that the polytomous variable makes some difference in the dependent variable. A SAS statement for such a statistical test is shown here as an example. NH Black, Hispanic, and others are names of 3 binary variables of race ethnicity. And, equals 0, at the end, means all of their coefficients are 0. But what about the reference category, NH White? Note that selecting a category as the reference category means that its beta is fixed to be 0. Therefore, the SAS statement that NH Black equals Hispanic equals others equals 0 means that betas for all of the 4 categories are 0, so there is no difference among the 4 groups. In this case, the p-value for the null hypothesis was 0.0419, so the null hypothesis can be rejected at the 0.05 level, implying that race ethnicity can make a difference in the fasting blood glucose level, controlling for age. Note that this p-value remains unchanged, regardless of the choice of the reference category. For this test, a quantity, denoted as uppercase F, is computed as a test statistic using this formula. This test statistic asymptotically follows a probability distribution called the F distribution, which is used for computing the p-value for the joint null hypothesis. There is another type of statistical test for linear regression. In this test, the null hypothesis includes regression coefficients of all independent variables in the regression model. The null hypothesis is that all betas, i.e., all of the regression coefficients in the model, are zero. To my knowledge, results of this global statistical test are shown in the output of any computer program of linear regression. In SAS, the table labeled Analysis of Variance in the linear regression output shows the results. In this example, p-value for the global null hypothesis is smaller than 0.0001. P-value from this kind of statistical test is usually very small, because the null hypothesis implies that none of the independent variables in the model makes any difference in the dependent variable, which is unlikely in actual research projects. In this test, the test statistic, f, is computed as shown here, and under the same set of assumption used for the statistical test of each regression coefficient, the test statistic asymptotically follows the f distribution. Mathematics of the f distribution is summarized in this slide, for those who are interested in the mathematical basis. And this is an example of the shape of f distribution.